We have one theorem in the differentiability function, that is continuity is a necessary but not a sufficient condition for the existence of a finite derivative. Finite derivative means differentiability, that is to exist the differentiability, continuous properties must satisfy. That is, I already told in while explaining the differentiability function, every differentiable function must satisfy the conditions of continuous function. That's I already told. That is the given here. That means every differentiable function is continuous. That is necessary condition, but it doesn't satisfy the sufficient condition. Sufficient condition means converse part is not true. What is the converse here? Every continuous function need not be differentiable. That is converse part. We can express this as, if f of z is differentiable, then it is continuous. At some point z is equal to z0. But converse is not true. Please write down this line because I didn't write first this line. Please write down in your notes. Next, see the proof. What's the given data here? F of z is differentiable. This is the given data. So, write down the given data here. That is, f of z is differentiable at some point z is equal to z0. Then, what is the differentiability formula? We have three alternative differentiability formula. To explain the continuous, I considered first alternative formula, that is limit of z tending to z0 f of z minus f of z0 divided by z minus z0 exists finitely, or we can say exists and unique. That is equal to what? This is the formula for differentiability. So it is, we can express as differentiability formula f dash of z0, that is f dash of z0 is equals to limit of z tending to z0 f of z minus f of z0 divided by z minus z0. This is the given data. Next, what we have to prove here? We have to prove this function is continuous. To prove the continuous, we should consider f of z minus f of z0. Why? Because we all knew the formula for continuous. See, what is the continuous formula? Limit of z tending to z0 f of z is equal to f of z0. This is the continuous formula. To prove this, we should have the terms f of z and f of z0, right? That's why I considered f of z and f of z0 terms, and also I considered the subtraction. Why? If I shifted minus f of z0 to the right side, we can get positive sign, because we should get positive f of z0. That's why I made subtraction. Next, we should multiply and divide z minus z0 term to the f of z minus f of z0. That means we should multiply and divide z minus z0 to the term f of z minus f of z0. That means f of z minus f of z0 is equal to z minus z0 into f of z minus f of z0 divided by z minus z0. That means multiply and divide the term z minus z0. Next, I considered here z is not equal to z0, because if I considered z equal to z0, this becomes, denominator becomes 0. That's why I considered z is not equal to z0. Next, taking the limit for both LHS and RHS as z tending to z0. That means apply the limit for both LHS and RHS as z tending to z0. Next, write the LHS side same as it is and then simplify RHS side only. See, RHS side looks like limit of m into n. What is the formula for limit of mn? See, limit of mn formula is limit of m into limit of n. That is limit of m into limit of n. Limit of m is z minus z0. Next, limit of n is f of z minus f of z0 divided by z minus z0. That means limit of m into limit of n. Next, if I apply the limit here, z becomes z0. Then we get what? z0 minus z0 is 0. Then this term becomes 0 into, see, it looks like differentiability formula. Differentiability of which function? Differentiability of f of z0 function. That means we are making the differentiable for f of z0 function. That's why I wrote this as f dash of z0 instead of f dash of z, because we are making the differentiation for f of z naught function. Next, 0 into anything is 0. So write the LHS side as it is. Next, shift minus f of z naught to RHS. Then we get positive f of z naught. Then it becomes what? Limit of z tends to z naught f of z equal to f of z naught. What's that? This is the continuous formula. Hence, we can say f of z is continuous at z naught. What we proved here? We proved every differentiable function is continuous. Next, what we have?